Hi, I'm Callum McCabe, and this is our Pico Hydropower project. So first we'll go over the location selection. The location we selected was Simon Conover's grandparents' house, which is a weekend and summer residence, not a full-time residence, and they're making plans to become more off the grid. As you can see, there's a large reservoir in the two images at the top right, and this reservoir has a natural drop-off, which can be seen in the satellite imaging in the bottom right. Um, this plan would improve the cost efficiency of this second home and could definitely help them out. So first we went through a preliminary design stage and we found a possible flow rate for draining the lake without over draining, as well as looking at the head that we would create with the drop off, and chose a turbine, which ended up being a Kaplan style turbine based on the lower head application. So in the system design, here's just a little overview. As you can see on the right, there are two images that contain most of the components of the system. But the five main components we designed were the intake, the penstock, the volute, the turbine, and then the draft tube. The image on the right is actually a slice through the middle, and you can see the components there. So first we'll take a look at the intake. This was designed with ease of installation in mind, as well as being able to filter out reeds and debris from the reservoir as to make sure there was nothing going down into the penstock. As you can see in the bottom right image, there is a grate on the front. You'd be able to clean it out and pull it off if there was any debris that made it inside the actual chamber. There's also a valve connected to the back of the intake that will act as an on-off switch. So if anything needs fixing downstream of this part of the turbine system, you can just turn it off and there'll be no flow going down through the rest of the system. For the penstock, this was designed to feed directly into the spiral casing or the volute. So as you can see in the bottom right or the bottom right of the image, it transitions from a circular cross section to a rectangular that would fit right up against that volute. And it has to travel around 70 meters, which is a lot farther than we originally planned, but we still think it'll be capable of obtaining the desired head and there won't be too much loss from the pipe friction. The diameter of the pipe we actually designed is around 7.9 centimeters, and this is to obtain that desired cross-sectional area for the penstock. Next, we'll look at the spiral casing. This was designed to redirect the flow into the turbine and also provide a housing for the turbine. And in the design process of this, 22 different points around that volute, the radii was calculated using an equation based on flow loss percentage, and this came up with our final design. Now for the turbine was designed based on the flow in the head of the system. And based on the situation, we ended up with a 4-blade Kaplan style turbine with central blade angles of 156.5 degrees. As you can see in the graphic, that is the rough shape of the blade, but in the full design, it's going to include curvature that flicks up at the top part of the blade and at the bottom part of the blade to better convert the power of the water. And we did calculations on this, and it looks to produce around 6.14 Newton meters of torque, which results in around 2.8 kilowatts of power production. But this is assuming pretty extreme efficiency, so it'll probably be lower than that in the final design. Next, we'll look at the draft tube. This was designed with a divergence angle of around 10 degrees, which allows the flow to exit the turbine and go into the tail race. And the final diameter at the bottom is around 16.5 centimeters, and this part is around 0.4 meters high, and it makes up most of the base of the turbine system, just under the volute. Here's our plan for prototyping. So most of the components we are looking to use PVC, and then we had three main objectives when going into this: making it low cost with available parts and having it be easy to build. For the turbine, we look to use a 3D printer for the complex geometry. And then for the casing, the spiral casing, we're looking to use acrylic sheets and epoxy. This will be the most hands-on part of the build because it requires us to laser cut some of the shapes with the complex radius, as well as using thinner pieces of acrylic and that epoxy to kind of wrap it around and create a sealed piece for that. Detailed to the right, you can see a list of the parts we're planning on using, as well as a total price, which is relatively cheap considering the complexity of the design. And then finally, we'll look at some manufacturing and installation plans to be made. So for the actual manufacturing, we're planning on casting for the casing and the draft tube, as this will allow for like very simple and quick construction of this complex shape. We won't have to be doing any metal bending or stuff like that, and the sealing will be a lot more simple. And then for the actual turbine, due to its small size and volume, we're going to look at machining it. And then for the pipe, we'll be looking at purchasing it at a nominal size from a distributor. We have a very long amount of pipe, so it'd be best to get that at a cheap price. In the installation process, we'll look to bury the intake under the gravel and allow it to filter straight in from the reservoir. And then it's all about stabilizing the actual main turbine component and making sure that weather or other aspects can't affect it. But yeah, that is our Pico hydropower system.